a little breakup of on Jeff's audio. So if you have that with me, you can get over in the chat window to let Jeff know. I don't know if it's on this end. I suspect it's on his end with his technical difficulty this morning. But today I want to give you a little bit of an insight into what we actually do and what manufacturers actually do and the things we look at to evaluate our own devices, how well they're working. And I'm very fortunate that we started a cleaning company the day that we started our, that we invented the system, patented the system, and actually started putting it out in the field, because essentially I have nearly 2,000 laboratories out there in the field where I can go look and see what's actually getting in these things. So today I'm going to show you a little bit about what we go through and what we look at. And I've got an article coming out on design here shortly. Jeff can tell you about that at the end. But design is a lot more than assuming an 80% removal rate or assuming your device is going to work like mine did in the field if you bought a device from us, or assuming that it's going to work like it is in the lab. I think there's a very, very serious lack of understanding of what washes into BMPs. If this understanding were in place, people would not be floating trash and vegetative material or claiming that vegetation was going to take up metals. It does a really nice job of doing that, but it also puts it in the food chain if you don't trap that vegetation. So anyway, let's go forward here. I'm going to summarize a little bit about what we find in our BMPs, and then we're going to get on and show you the fun stuff. To me, the fun stuff. I'm privileged to be able to look through a dissecting scope or a macroscope and try to analyze what we see. The common materials we find are the total sediment load. I've advocated that term because people say total suspended solids. If you read the definition in Management Measure 5, it says that that would be actual suspensions. It would be material that can be suspended up in the water column. Material that saltates. Saltation is the bouncing along the bottom of a bed by a particle that can't quite get airborne, but it is rolling or moving or creeping. Sometimes it does actually bounce. Or bed load. And we have people today that take TSS to mean what's actually suspended. And the EPA test TSS actually pipettes out suspended particles. They won't be suspended long. They have to be agitated to get us. But anyway, total sediment load is really what we're looking at, because that's what's going to stop in your pond. That's what's going to stop in your sand filter. And that's what's going to stop in a manufactured device if it's sized properly. We have trash, debris, and litter. We have vegetative material. A lot of the trash is paper products, which is made out of vegetative material. A lot of the other trash and debris and litter is plastics, which are very slow to break down. The paper break down that quickly. We have oil and hydrocarbons, of course. Along with running vehicles across our roads and sites, we're going to have that. And then secondary pollutants that attach to the sediments, attach to the trash, attach to the vegetative material, and attach to, believe it or not, to the oil and hydrocarbons. That helps put them together as kind of an agglomerate, which will bind them. Now what we find varies. Remember, we're dealing with a system that flat rates every BMP, every site, every time, and for the most part. There are a few places that say, hey, you can't use infiltration unless you have pretreatment. But if you do use it after pretreatment, we'll call those two things together 80% or 85%, or there's some phosphorus removal, nutrient removal rating there. But in reality, what we find out on the sites is very, very much different materials come into the sites. And it's intuitive, and it would be common sense to understand that a BMP that caught all of large particles might not catch all the small particles. So we found a lot of things. There's the site flow versus the flow the BMP is designed for. Some BMPs bypass, like a 4-bay, or like a product, manufactured product designed to bypass. Some don't. But each one of those BMPs, whether it's a large pond or a small 4-bay, are designed for a certain flow. And depending on what the flow has been recently, you may find something different in the bottom of that BMP. Or depending on what the antecedent conditions have been before a storm, you may find different things washing off, even though the flows are the same. Total site acreage makes a difference. Larger sites tend to attenuate peak flows. the time of concentration, a short coupled site would peak faster and generally have more energy. The site usage obviously is a big deal, whether it's commercial, office, residential, parkland, who knows. The percentage of impervious surface has a lot to do with how pollutants are delivered and which pollutants are delivered. And then the upstream conditions. Are there upstream flows coming on? Is there a bypass in place? Or is there a detention pond above it? Just some brief review here. Most of you who come to my webinars have understood this concept a long time ago, but you know, this slide right here essentially says smaller you make it, the better it works. And all of us are held to sizing standards. Usually we set them in the lab or we set them by field test. And then we adhere to those more or less depending on the usage. Some manufacturers are better at adhering than others, but you know, that's also true with engineers who design wet ponds. Quite often the effort is to minimize flows, use the lowest range of curve numbers or C factors to make a pond smaller, but the proper design percentage and the size of the BMP really does make a difference. And if you're looking at water quality, it can be a critical factor. We have found over time that the delivery off of smaller sites in general, and I think it's because they have more intense usage, but there's other factors. It's because they're generally steeper, generally more energetic, generally have more traffic trips, generally have a lower percentage of roof to parking lot, being commercial, higher parking ratios, that sort of thing. They generally deliver more material than the larger sites. And this trend is something we've tracked over time. This is about 6,000 maintenance operations here that show you how that material changes. This is another plot of impervious. Obviously, you can't get over 100% impervious. So there's a big stack of materials over on the right-hand side of the graph. Those are the 100% sites.
Hey, John.
Yes.
I think you have your screen paused and your slides aren't advancing.
At all?
No.
All right, let me take a look here.
I just got a comment from Boyd Church on the same thing.
All right.
Now I can see the current graph.
All right, good. Thank you, Boyd.
Can you try clicking? Do me a favor, try clicking forward and backwards real quick.
I got you. I'm going to go back.
There we go. There you go.
You don't need to hear the pros again, but let me show you these charts quickly. This is the amount of sediments versus total acreage, which tends to drop, as I was just saying, as you get larger sites, for the reasons I had stated previously. The amount of loading versus impervious tends to increase. If you look generally at the trend line in there, that trend line is an average line. We see the loading from small sites going up, small percentages of impervious going up and up, and the tallest points on this graph come from 100% impervious sites. But there's obviously a definite trend, which if you increase impervious, you increase the loading. This is a plot of bypass versus non-bypass. The blue dots are the non-bypassing systems. Now, this could be good and bad. If this were a 4-bay, you certainly wouldn't want it necessarily to be too full, or a pond to be too full. So you'd like to have it bypassed, and the blue dots could be the 4-bay, which doesn't bypass early on. But the idea is to let you know there's differences in how you protect your BMP from high flows or low flows, or when you cut off the flows. Cutting off the flows early can cause you to catch almost nothing. And this chart here, which is pounds per acre per year over as the height of the bars, and listing the different types, shows you, and I won't go through them all, but overall we average about 5,000 pounds per acre per year. But some things like high-rise urban residential have much as 10,000 pounds per acre per year average. And there's great variability. So this variability of just the gross amount of material is reflected in what you see in the BMPs. Now, separators, there are two types of BMPs. I wrote about this in 2004. I did not call them separators. I called them gross pollutant or hydrodynamic devices that depend on settling. And then I talked about devices that could catch smaller particles like infiltration practices, large wet ponds, constructed wetlands, things like that with a very low energy gradient through them. But separators today, people have come to call, there's two types of devices, separators, and they call them filters, but they're not really filters. They're media-based devices, most of them. And the reason is a filter that would catch 20 or 30 micron particles would clog so quickly in stormwater it would be worthless. And so we use things like perlite that we expose the flow to that has a porous surface that can catch it. So separators, though, are usually tested with materials that average about 100 microns. If you look at regs around the country, they may call these pretreatment devices. They may call them a certain type of BMP. South Carolina DOT calls it a type 1, with a filter being a type 2. I think a catch basin insert is a type 3. But OK110 was what was traditionally used. It's no longer available. There's other particles, test particles that are out there. And there's actual business built around having graded sand. And it's very useful in the ceramics industry and other things. So 100 microns for those things. When you want to add smaller particles to the text mix, now New Jersey has done this. They've added SilicaSil 106. Now this is a ground silica, okay? And when you get down to the filter or media-based devices, they usually use more of the SilicaSil 106, or they use all SilicaSil 106. SilicaSil is made by U.S. Silica, so is OK110. There are other products out there made by other mining companies and aggregate companies. So the average particle size of the OK110 is about 100 microns. Average particle size of SilicaSil 106 is about 23 microns. Settling speed, all other things being equal, if you're talking about small particles, works off the square of the radius. And so if 23, if we made it 25 and 100, 1 to 4, OK110 would sink about 16 times as fast as the average particle in SilicaSil 106. Meaning you might need a device 16 times bigger to capture all of the 25 micron particles. OK110 is made up of natural rounded grains. I'll show you some in a minute. And SilicaSil 106 is ground silica. It comes off of a source of rounded grains, and then it's crushed and processed and sorted and to come up with a consistent product with a consistent particle size definition. Now, most people have no idea what 100 microns looks like or 23 microns look like, and hopefully you'll walk away today with or tune out today with an idea of what those are. Now, I will tell you that the head of I won't mention him now because if he were in the room, I'd mention him and have him comment, but he's not. The head of the MPDES division of the EPA looked at 100 micron sand one day at my booth at StormCon and guessed that it was 4 microns. So don't feel bad if you don't really know much about grated silica or what a micron is. It's a thousandth of a millimeter, a millionth of a meter. But what does that really translate to something we can get our hands on? There's a little strip at the top here that I'm going to use as a calibration, so you can, and you look at other slides, you're going to see those 110 grain particles. This is approximately 100 micron sand, and the particles are rounded. This is on low res. There's a bunch of them that are on the slide. This is the same particles on high res. Now, the actual resolution you see on your screen or that I print out, I do have some slides where I have little measuring lines and you can see what 90 microns looks like, but we're just going for visual impression here, and this is what OK110 looks like at high rise. Every slide I show you at low rise, pixel to pixel, is exactly the same resolution. So these slides are comparable. And you can see even within this OK110, there's a large particle over at near the middle, slightly to the top right, that is probably 150 microns, and there are some 75 micron particles in there. But this is what OK10 looks like, and I've got a test strip at the top so you can get an idea. This is back to low res again. This is OK110 dropped on a penny. You can see the BERTY of Liberty there in part of Lincoln. This might give you a 100 micron particle can easily perch on the leg of the E or the Y on a penny. It might give you a little bit of a concept. Now, this isn't meant to brag. I just want you to understand something. We caught 98% of the 60 micron particles and above in the field for an ETV test in Griffin, which a lot of jurisdictions don't think is good enough. But this can give you an idea of the size of the particles you're dealing with. By the way, most separators can do that without a ton of trouble. This is OK110 on a penny again, and in this case I put it on high res, and it can give you a little bit of perspective. You got a penny in your pocket, you might want to pick it out and look at it. It wouldn't look like dust necessarily, but it looked pretty darn close. This is much smaller than beach sand, and in fact it's so dusty you have the material safety handling data sheet has a warning for silicosis on this. If you work with this stuff every day, you could get what they call miner's lung from silica in your mine. This is SilicaSil 106 on low res. You can kind of contrast this to the OK110 low res, and I've got at the end a test strip at the top. The tiniest dots you can see are in the 2 to 5 micron range. I don't know if you could really see it too. The tiniest things you may be able to see on your screen are about 2. And I will show you this on high res right here. This will help you some. There's a test strip at the top, and it's important for one reason. On the test strip, the rightmost large particle is about 50 microns. The almost middle particle, middle-sized particle, is 25 microns. And the smaller particles are smaller than 25 microns. You can see that SilicaSil 106 does have some almost clay-sized particles. A geologist thinks clay is a micron. There's arguments among soil scientists and others that it's 2 microns, maybe 3, some people, but suffice to say, this is pure silica. Silica is heavier than clay. It has a heavier specific gravity. So there's a good bit of small particles. SilicaSil 106 tends to clump, and so you see these particles gathered together here. And this is actually, it imitates nature pretty well because particles tend to clump in nature also. In fact, but one of the challenges of evaluating particles under 60 or so microns is getting them separated where you can actually measure them and get them out as a group. This is a real field sample. This got the OK110 and SilicaSil 106 at the top in for your test strip, so you can see. This is pretty much the average size, particle size distribution we see coming out of the field. Jeff, are you able to see my screen arrow here? I don't want to change to the other arrow if I can help it. I think Jeff turned his mic off. Well,
yeah, John,
below the test strip on the top right.
John, I can see your cursor.
My arrow is on a little, good. And there's a little piece of organic sitting right here. There are some other organics scattered around. This is on low res. You'll see that there's a lot of variation in the shapes of the particles and many, many small particles contained inside of this. This is high res, and I'll give you a little bit of definition here. Once again, you look at this OK110 up at the top, and you can see that this particle over on the lower left is about 80 microns maybe. This is about 150 microns over here on the right. And you can see that there are a good number of small particles in here in this average sample. Most of the particles here are sub-rounded. This probably indicates that they are coming from a manufactured sand or a purchased sand. However, there's a good number of angular particles in here too, which indicate there might be some natural source material that's contributing to this. The colors are natural. Here's a nice piece of organics up near the top here. So this is pretty typical of what we have. If I had to pick out an average slide, I'd say this is pretty close to average of what we have coming out of our sites. This is a large particle size distribution, which would indicate that there was a lot of man-made or amended soils, and we'll talk some more about that in a little bit here. But this is very high in organic content, and this is on a low res. Looking up at the OK110, you can see that this piece of pine straw, it looks like here, is about a third of a millimeter wide. It's a piece of organics. There's lots of smaller organics in here. But this is a little more interesting slide when we get up to the large particle sizes. Here I put the strips at the bottom so you can see a little bit of the organics that are in here. There is a distinct pattern of rectangular grains in here. Now, these are not natural. This is not natural quartz. You can see that there's small particles distributed on the face of these. This is an unusual sample. I don't think I've seen this in 1 out of 100 samples, where we've got some artificial material, probably man-made. It could be coming off of the material that's used to build brake pads. There's a lot of other possibilities there without some detailed spectral analysis and some other things. This is difficult to tell. But these are much larger particles, and we've probably got an average 200 micron particle size definition here. That type of material is the type of material that a separator would be very good at. This slide here is, again, a large particle size definition. It comes from natural soils. Now, what I mean by that is this particular separator was on a site that had probably 1/2 of the area was natural soils washing onto the site. We're high res, so looking at the test strips at the top, the OK110, you get an idea of the size. This little orange guy here is probably 100 microns. There's little pieces of organics, which is probably part of a root here. But notice the angularity of the particles. There's a mica grain probably right here. There's mica all over this slide. There's grains of feldspar, which have a distinctive crystalline shape. But there's the silica that is here is not clean. It's not shiny. It's not easy to see through. So this soil had a low sand content. This would be similar to a Appling soil or a Cecil soil in Georgia, Edneyville, North Carolina, that sort of thing. Fresh material, full of minerals, a lot of that coming to the site. There is, however, a significant amount of man-made material in here also. Some of these pieces in the middle, in fact, a very large piece in the very middle of the slide here is either a piece off of asphalt, it might be, but it's definitely an agglomerated piece that's not natural that's occurring here. This is the same slide on high res. I think I can show you pretty well with this being a natural crystal. And the quartz that's in here that exists is fairly angular, although there are some rounded grains and some consistent material that would be a lot more consistent with amended soils or constructed soils. Also notice that there's a much higher percentage of small particles in the background here, a much higher percentage of clay and silt in this material, and a fair amount of large organics off to the side. The streaks you see here are part of the, we use different types of backing material. This is a black backing material, so they're not a part of the sample here. This material came off of a small commercial site. This is probably almost 100% constructed soils, amended soils, places where the landscape folks brought in vermiculite and peat and whatever, whatever they needed to do for moisture content. They bought sand, they mixed it, and they wanted to have drought-tolerant soils and urban-tolerant soils to put in their flower beds so that everything grew nice and looked nice. If you look at the particle sizes here, you've got 1,000, 2,000 microns. This is really, really large compared to the stuff that's coming off natural soils. There may be a little of that in here, but we have particles under my cursor right now. It's kind of the center right is a piece that's come off of asphalt. There's some more asphalt over here, it looks like. Some of these other agglomerates could be iron, rust. There's paint chips. There's other things in here. There is a little bit of natural mica. I think some of this mica is vermiculite mica that was added to the soils to help amend the soils and make them a little bit lighter and make them not compact so well. Remember that on a site like this that's built, the site starts out generally by being cleared. The specifications usually call for it to be compacted to 95% or 98% of proctor, which means that the soils are packed where they will bear well. Then the building foundation is done, the footers are poured, and the building is done. There's rock put down, there's asphalt put down, islands are built. There may be a little 2-to-1 slope in or out on one side, which could be where some material is coming here, some of this angular material like what's under my cursor right now. But these sites have almost no native soils on them. And this is pretty typical. Now remember, this is low res. When we look at this material on high res, it's almost shocking the contrast between what's coming off of a small commercial site to this 50, 25 micron Silcasil 106 test strip up here so that you can see what the sizes are. This is part of the explanation. And by the way, under my cursor now is a nice piece of asphalt. You do see some small particles adhering to the surface of these larger particles. You do see, now there's a depth factor here, so out of focus in the background, there are some smaller particles that are reflecting. This one's reflecting some red light. But my point here is this is part of the explanation of why smaller commercial sites tend to have higher loadings and higher delivery because they have larger particles. And part of what we can start to infer is that we might not have to be quite so careful in our sizing on high-use commercial sites, small sites, as opposed to larger sites. Another thing we could infer, if the BMP is undersized, that the small material is just simply washing out of this device. Now, I know where this particular sample came from, and the device is not undersized, but if it were, this would look very similar. There would be almost no difference. It's hard to tell without knowing the engineering data on the site. That's part of what the value has been of having the engineering data and tracking our devices. But let me say this: the variability is still so great. It's in the materials that are used. Always tell the story of compare a 1-acre dentist office to a 1-acre gas convenience operation. The material that comes off of them is not going to be the same. The amount of organics is not going to be the same, and certainly the traffic rates. 1,000 trips a day to the gas convenience store, maybe 10, 20 to the dentist office. All of these things go into what is coming to a BMP. Now, since I'm in the manufacturing business, I tend to think of things in that way, but it's just as important if you're designing a sand filter to think about whether or not you need to protect it and how much in the way of small material is going to come to it, how quickly a pond's going to fill. This material here came off of one of our one of our coconut fiber filters. It was literally shaken out of the filter onto a tarp where I could gather it, because I wanted to show you what happens with small particles when they encounter organics. Almost everything here, and again, get your perspective at the top, looking at the OK110, we're low res here. So we can say this is probably a 500 micron a piece of pine straw or something similar, grass blade it could be. This white piece in the middle is a piece that is decomposing, that is coated with either a fungus or bacteria. It's hard to tell from what we're looking at here. It's definitely got bugs growing on it. That makes it kind of fuzzy looking. As you can see around it, the rest of the slide's in focus, so you can get kind of an idea there. But all over this organic material, stuck to this organic material, and stuck quite well, by the way, are small particles. These are getting in the range of the dots you can see are probably 20, 25 microns. Some of the particles obviously are bigger, up to 100 microns. Here's the same slide on high res. The tiny dots that you can see here on the surface of these pieces of organics are in the 3, 5, 6, 8 micron range. I don't know what this red dot is right here. It might be organic or it might be particulate. You can see much better, of course, under a scope when you're looking, and I try to get some representative stuff. You can see there are things going on the surface, on the surface of these organics. This is some material. It was in the coconut fiber, so it was underwater, not trapped in our basket, so it stayed dry. There's definitely some surface decomposition going on here. There's a lot of things going on here, but one of the things that's going on is that small particles, and we know that metals and other things are being, because we've analyzed the fiber, are being attracted to these organic surfaces. This is where the chemistry is taking place. It takes place on the organics. So the organics, which are almost the same buoyancy as water once they're decomposed, are in the bottom of these ponds, or they're in the bottom of a device that doesn't screen them out. In this case, we could have missed them with our basket. Remember, I'm using 1/4-inch mesh, so obviously that's a lot of microns. That's about 12 millimeters, I think, so that'd be 12,000 microns. We're not going to catch tiny particles. Things that come to us decomposed, we're not going to catch. So this coconut fiber filter helps. The coconut fiber filter helps us to trap those sort of things. But you can see where if these things are almost neutrally buoyant, and you can prove this to yourself, just step into a pond or go to a device that doesn't have a trash screening mechanism and let it and put your foot down in the water, and you'll see a cloud of organics come up that'll stay up in the water for 30 minutes, an hour, maybe 2 hours. You can walk across a wet pond in waders and see the trail for a long time. And there's a lot of things attached to these organics that are important things. So this is a mixed source area. This is what I'd call a variable particle size definition. When I see this kind of a sample, if you remember, the very first slide I showed you was fairly uniform. And it did not have much of this big stuff here, this 1,000 or 1,200 micron stuff. It was very much more like the uniform area here, very, very uniform. That would indicate that there is a low energy site delivering that consistent product, so to speak, and it would indicate that the site is very homogeneous. Maybe one type of surface, one type of landscaping, maybe just sodded lawn and pavement. This site is a little different. It's got a mixed source area, and it's pretty obvious from looking at the organics, the large particles, and the tiny particles that there are different source areas that are contributing here. There's some interesting, very clear, washed processed sand here. There are angular, this rounded. That generally comes out of river sand. It's generally dredged or mined. There are other, there's fossil sands, I would call them. OK110 is, this stuff here is a rounded grain that occurs naturally that they mined.
John, you got one question here?
Sure.
I don't know if you can see it or not, if you can pop it up on your window.
I could. let's see. Got to expand my window. Is it possible to find clean sand as it is sometimes specified? It may be better to use dirty sand, take advantage of the residual Fe iron. Yes, absolutely. Boyd Church, you're exactly right. The sands that we buy sometime, I'm going to put that window back down. The sands that we buy sometime are not the best sands. Natural organics and natural sands that have a high mineral content, a higher mineral content, especially of iron, can be useful. We have that higher iron and manganese and content here in Georgia, and that's a good point. This large item at the bottom looks like it's made of very fine particles, and it looks like it's homogeneous, and it would tend for me to think this is a man-made piece. It doesn't look like a chip off of a rock. There's no grain orientation. It's hard to imagine that that's a natural piece. So that could be a paint chip. I know you would think paint would not look that way, but it certainly can. It could be a metal chip that came off of a car, iron rust, that sort of thing. There's some organics in here, but this type of material with the different shapes, the obvious different sources, essentially came from a mixed use, a multi-use area. So to give you an idea of how these things should work, I went to a mountain stream, and the reason I went to a mountain stream is it would give me some fairly fresh material that had just, and this is just what Boyd Church was talking about, that had just come out of, this came off of essentially a mica schist that had a fairly high percentage of quartz in it. So there's a little bit of sand coming off of there. And if you saw this as a residual soil, and remember, this stream isn't just carrying residual soils. The residual soils are generally held down pretty well by the undergrowth, forest and grass and that sort of thing. But if you saw it as a residual soil, it would start out as what we might say is a sandy loam on the surface, maybe 40 to 50% sand, and then and maybe 30% silt and 10% or so clay. Maybe a little more silt, a little less clay. As you went down in the soil series, as you dug, you would find a higher and higher content of clay. And the reason for that on the surface is the topsoil areas, the clay has washed out, leached out over time. And so the sand is what remains. But looking at this under low res, it's fairly reminiscent of the material I showed you in the first slide. There's a little more variety here. It's not as homogeneous, and there's a little bit more variety. But looking at it in detail, these pieces right here, the ones of the lighter color, the ones that are opaque, in general are feldspar, microcline. There's a couple other things they could be. The black here, and some of this black is biotite mica. Some of it is magnetite or tourmaline. These are fresh, what we call mafic, heavy minerals. They do have metal content. The quartz grains are generally clear. Because this is a stream, we have some that are sub-rounded. A geologist would call these sub-rounded. We would call some of these subangular, but the fresh material is definitely very angular. And there's a good bit of the clay-sized particles in here. And some of these materials that look a little brown and nondescript are actually still residual pieces of the rock that haven't quite separated out yet. They're in the stream. They're fairly fresh. And they're on their way to becoming beach sands eventually one day. The other material will be cleaned out, washed aside, carried away, settled out, and what will remain will be more rounded sands that eventually make it down the stream through the reservoirs and to the beach. So to give you a little bit of summary about what we found in our materials and a little bit about what it means to me, the number one takeaway from this should be, and this is a point I'm trying to make, remember, I get approved in areas based on my lab testing. You know, that's great. It doesn't mean the system is perfect. It means we need to point out problems where they're there so that we get smarter and over time learn to test better. Real sediments are nothing like laboratory test materials. You've seen them on the strip at the top. You do know, you can observe that the Silica Sil 106 is probably more like what you're likely to encounter in the field than the OK 110. You didn't see very many perfectly round, highly rounded silica particles. We know for a fact that the density of field materials is about 1.7 times as heavy as water, and the density of silica is 5 times the density of water. We know that the angularity of the particles has a seriously high effect on the settling rates, as rounded is easier as opposed to angular being tougher. There's a lot made of surface area. Oh, clays are important because they carry the most surface area. Well, first of all, you're not going to settle a clay out of water ever. And since it's a micron or two, you're darned unlikely to filter it out either. But the neat thing is particles that size like to stick to other particles. And the more rough the surface of the larger particles, it's very easy, and this has been proven, and I didn't do the research myself. There's 2 or 3 papers out there if you want to look them up that shows that on average 30 to 50 micron particles in nature have higher surface areas than the more rounded clay particles at 1 to 2 microns. And the reason is that obviously with a rough surface, you get more surface area. So the number one thing to realize is that we have to have a level playing field. So we've standardized our tests methods. But if you don't test everybody with the same mix of sediments, you can't possibly have an apples to apples comparison. So that's why we do it that way in the lab. We can control the flows, and the flows in the lab are nothing like the flows in the field. They don't stay constant and monitored in the field. But that's the number one thing, is that real sediments, what you saw today, are nothing like the laboratory test materials. Second thing is that site characteristics vary greatly, and I believe, and that affects what washes off of them. I believe we need to do a lot more work to figure out where, if you go to a standard manual, let's just say in North Carolina, you'll find 4 or 5 or 6 practices rated at 85%. And the engineer can pick what he wants as long as he picks the right practice and builds it the right size, length to width or depth or surface of sand fields or whatever, he gets an 85. Well, those practices are not the same. I don't care that the number's the same. They are not the same. They don't work the same. And having a lot better knowledge of the materials that wash off the site, this is the problem. Most designers have never seen real materials that wash off the site. They have no idea the particle size distribution. And I'm not picking on anybody here. I'm just saying it's a fact. And worse yet, the people that write the rules have not seen real material. So there's a time for a sand filter, and there's a time for a wet pond, and there's a time for a constructive wetlands, despite the fact they're all rated at 85%. And as an industry, we need to get better at knowing that time and knowing that place to apply the right device. There's also a time for a manufactured product. There's a time for a lot of media with a tremendous amount of absorptive capacity, to a lot of zeolite, a lot of activated charcoal, because of the nature of what's coming off the site. You know, we've found that we're getting very impressive metal and nutrient removal rates by simply using humic material, organic material, coconut fiber, and being able to collect more organics as we go along on that fiber. But all of those, everything has a place, but they're certainly definitely not equal. It's important to remember that background soils are not involved on most sites. It is just amazing to me that places like Georgia, the Georgia Technology Assessment Protocol, GTAP, says, oh, you got to get a test for each area based on the background soils, as if there were a lot of background soils on most commercial sites. This affects me directly, but the point I'm making is, even on sites where there are background soils, a soccer field, there has been strict attention paid to the upper level of that soil, and it has been planted, and it has been stabilized, and the drainage has been controlled. It's a different thing, and we try to fight erosion all the time. And erosion is what will give you your background soils. It's a little silly to base all your designs on background soils, but there's several states that do it, and it just doesn't make a lot of sense. Now, it does make sense if you're in Savannah, Georgia, on the beach, or Destin, Florida, or Virginia Beach, Virginia, to look at your background soil and the distribution of the material that's going to be tracked onto your site, that sort of thing. Organic content, it's amazing how much it varies. I suspect it varies on how much stuff's being blown into catch basins, but there's a wide variety of the amount of organics, both gross, leaf trimmings, that sort of thing, and finer organics. And secondary pollutants, you can see in almost every slide I showed you that there are small particles attached, particularly to organics, but also to larger particles all the way through in what we find. So hopefully today you got a little bit of a look into my laboratory and what drives us to try to improve what we do. You know, I'd be less than honest with you if I didn't tell you that there are places I'd like to revisit where I put a device that was larger than it needed to be based on what we're seeing, or where I didn't get a device quite large enough based on what was coming off the site. There is, I believe, a partnership needed between engineers, regulators, and manufacturers, and if you will, the manufacturer being the guy that builds the pond or builds the wetland, or the guy that manufactures a product like mine, to hold closer to the original design. Similar to the way you could substitute whatever 85%er you wanted to in North Carolina, quite often BMPs, manufactured BMPs, are substituted as if they were all the same. And that's fine as long as nobody's paying any attention and everybody's going to use lab results and flat rate them. But let's say you had a sensitive area, a trout stream, you spent a lot of time with an engineer, you were very concerned about the nutrients coming off the site, you're very concerned about the organic content, and you built a system, a manufactured BMP, that would handle a lot of trash and debris and was oversized compared to what the normal particle size distribution for testing would be, because you've looked at what's coming off the area. And as a manufacturer, I can almost guarantee you'd never get that job, because someone would come in, quote a test, take the job away. Look, every manufacturer does it. We all look for business. But I'm saying as a group, as an industry, as we go forward, we need to strengthen that bond between the designing engineer or the design professional, the jurisdiction, so that it doesn't have to be a specific device or a specific thing, but so that the specification of performance is written more closely, and we get better performance. That's if we really want to do our job in water quality. And I will take some questions now. I'm going to hopefully freeze this and take a look at chat and be happy to talk with you guys. I wish I could have a better resolution screenshot. I'm looking for a better scope cam that would help you see at the same resolution in 3D like I can through the scope. But I think this does give you at least a glimpse into what materials are like to come washing off of our sites. Jeffrey?
All right, John. Looks like you got one question specifically up here right now. Mr. Selbig in Wisconsin, USGS states that due to certification error.
Okay, I may have put Jeff to sleep out there.
John, you there?
I'm here.
All right. You got one question here from Boyd again. Mr. Selbig in Wisconsin USGS states that due to the stratification error, most of the testing of BMP efficiencies are incorrect. Any comment?
Read that to me again.
Mr. Selbig in Wisconsin USGS states that due to stratification error, most of the testing of BMP efficiencies are incorrect?
If he is talking about lab testing, I would say that is not a correct statement. If he is talking about field testing, I would say it certainly is. I'll expand on that just a little bit. In the lab, if you know you're feeding 200 milligrams per liter of a mixture, let's say half OK110 and half sickle cell 106. The OK110 will tend to ride a little lower in the water. The sickle cell 106 will ride a little higher in the water. You have to set your sample points. Usually there's 3, sometimes there's 4 tubes. They're called isokinetic tubes. So the isokinetic means the water, the sediment entering the tube doesn't have any more resistance to entering the tube than it would going around it. You want a zero pressure rating there. But isokinetic tubes, and you have to move them to be able to get a consistent reading within 5% or even 10% of 200 milligrams per liter. That's just a fact. It's very difficult. When you go out to the field and you throw a sampler tube on the bottom of a pipe, or an inch off the bottom of the pipe, or 3 inches off the bottom of the pipe, it is not possible to get a consistent reading of the sediments. Now, going back to the lab, if you slow the water down, the sediments are going to be in a different place. You got to change your tube. If you speed the water up, sediments are going to move higher and be distributed differently. In the field, there's no way to judge that. But one thing Mr. Selbig doesn't recognize in his question is that it's really meaningless to talk about percentage of removal. What you need to talk about is the effluent concentration. And here's why that's important. In the laboratory, on the back side of the device, when most of the large particles are gone and there's been really good mixing, it's really easy to get an accurate reading. The materials are much lighter. They're evenly distributed in the water column. This is common sense. In fact, since you don't know the concentration coming out the back of the BMP in the lab, you have no idea where to put whether your readings are right or not. This is why in the laboratory, most people do what's called mass balance. They feed in 500 pounds of sediments. They still test the influent to see what the concentration is. They still test the effluent, but when they finish, if they've got 400 pounds in the device, they had 80% removal. What they have found from doing that is the effluent readings are very much, or have a much greater accuracy, whether the tubes are high or low or whatever. So if you go to the field and you get an effluent reading that's good, I think in Highlands, North Carolina, we averaged 11 milligrams per liter. That was fabulous. Anything under 40, I think, for a separator would be good. You probably want to be in the 20 to 25 range for a filter. But it's absolutely true that stratification is the arch enemy of accuracy in field testing, and that matched pairs of samples, that's a whole nother issue. How do you find water coming out that was equivalent to the water coming into a device? How do you match those two pairs? So, boy, that's a great observation.
And yeah, he was referring to field testing with automated samplers, and something else to point out, John, that St. Anthony Falls Laboratory has done some testing with floating samplers, so to adjust for the flow stream.
Well, there's some better ways to sample. There's no doubt there's some better ways to field sample. It's just what's the word? The common practice has been an automated sample system tied together, 14 to 18 bottles, composite samples in the storm, suck up water in the front, suck up water in the back. It's cheap, it's fairly easy, and it's less likely to fail. The USGS, if you go look at their sampling methods, in-stream sampling methods, they've got a lot of columnar type samples and some samplers and some other things. That technology, however, is much more difficult to to modify to make it work with a sampler and a pump. So those are generally grab samples, field samples that are taken by a practitioner out in the field, which, by the way, is how our device was sampled in-house. That's a great observation, boy. That's, you know, I'll say the same thing about field testing as I do lab testing. Lab testing gives you a level playing field. Field testing is one site, one time, and my goodness, I tested a 1056 in Griffin, Georgia, and I've been approved all over the country in all kinds of sites, particle size distribution, larger machines, smaller machines. But a field test does give you at least one glimpse. If the methodology is similar, like they did in the ETV testing, then you can think the results might be comparable, but the sites are never going to be. But the other thing is it does show practicality. And practicality, there have been some great solutions that have been advanced. I'm not going to mention any of the ones that are having trouble, but some of them, you just can't keep them running. And even though it looks really good in the lab with Silcasil 106 and OK 110, you put it out in the field with trash, debris, oil, vegetative material, the kind of fine material that you saw coming, and they run for a week and they quit. After that, they're on bypass. And that's why a field test is important. And you're right, it's a crapshoot. I won't say a crapshoot, that's not fair, but stratification's a problem.
All right, any other questions? It seems to have quieted down a little bit, Jen. Thanks again for your time. If anybody does have any other questions or after the fact, you can email jbenty at crystalstream.com or John Mall at crystalstream.com. And we'll be sure to get you back your answers. If you don't forget to don't miss our next session on July 12th at 1 p.m. What should you look for in a stormwater maintenance company for your project? Till then, thank you everybody, and hope you enjoyed the webinar. Have a great day.